Hello everyone, welcome to the course on Fundamental of Electronics Engineering. This is lecture 2 and in this lecture we will see what are enhancement type MOSFET. In our last lectures we have seen that MOSFETs are metal oxide semiconductor field effect transistors and they are having high input impedance. So that means if they are having high input impedance, so they get the advantage over the conventional FETs. So the MOSFET are best suitable for the amplification. And also we have seen in the last slides in the depletion type MOSFET that the switching speed of the MOSFET are quite high in comparison with the slow operations of JFETs. So these advantages of MOSFET will make the MOSFET suitable for various type of applications. So MOSFETs are used in the analog circuits, analog and digital circuit both. MOSFETs are used most frequently as compared to BJTs because they are having numerous advantages: the power consumption, the high speed. MOSFET are mainly used in the amplifiers because of their infinite input impedance. This is a very important advantage of MOSFET. So it allows the amplifier to capture nearly all the incoming signals, because in amplifiers we need to capture the signals. So the MOSFET performs better as compared to JFET and BJT. So we have the second type of MOSFET is the enhancement type MOSFET. So as we have already seen in our last lecture that in the depletion type MOSFET, the channel was already present during the operation phase, whereas in the enhancement type MOSFET, the channel was absent and the channel will be formed during the operation. So first of all, we will be seeing the construction part. So we can say that MOSFET, again enhancement type MOSFET, is a 4-terminal device. First is gate, source, drain and substrate or body. Substrate and body. Also, we can say that here the channel was absent, means no channel was there during the construction part. We have the SiO2 layer. Again, the aim remains same, that it acts as a insulator between the gate terminal and channel, or we can say gate and the substrate or body. With the help of metallic contact, we can define the terminals: drain, gate, source, and this side we have body or substrate. So first of all, we'll see the type of MOSFET, type of enhancement type MOSFET. So they are N channel and P channel. So as we are aware, this N and P channel is a region basically between the drain and source terminal. So for N channel depletion type MOSFET, and this doping is of the material is of N type, and the channel which will be formed during the operation, that will also be of N type. So the major difference, we can say that the channel is absent like this. So this MOSFET includes 3 layers, as we have already seen: gate, drain, source. The body of the MOSFET is also known as substrate, that is internally connected to the source while we are seeing the operation. In the MOSFET, the metallic gate terminal from the semiconductor layer is insulated through a silicon dioxide layer, SiO2 layer, or it is a dielectric. A substrate, basically the body of the substrate, also give the physical support to the device. So this is the construction part. Now we will see the operation or the working part. So again, if we can see in the construction part that we have 2 terminals. We have, let's say, gate, source, and we have drain and source. Means we need to apply the voltages. Means we are putting the biasing to see the operation or the working of the particular device. So first we have gate to source voltage, VGS, and also we have VDS. VDS is between drain and source terminal, and VGS is between gate and source terminal. So we want to see the effect. How we can see the effect? That first of all, we'll be fixing one value and we'll be varying the other. So first of all, when VGS is equal to 0 and we are applying some positive voltage. So what will happen? VGS is 0 and VDS is applied. So it will attract the electrons. But since the channel was absent, if the channel was absent, so no electron will move from source to drain side, and as a result, the current ID equal to 0. So that means we can write here that as VGS is 0, and we are increasing the value of drain to source voltage, the width of the channel was 0, right? Channel was absent. And if the channel was absent, right, so no electron will move from source to drain side, and as a result, the drain current ID was 0. So the question is, what is the minimum value of gate to source voltage to establish a channel? So we have the solution that will be fixing some threshold voltage. So this is a circuit that when VGS is 0, we can say that no electron, the channel was absent, no channel was there, and as a result, the current ID was equal to 0. So the minimum requirement to for the flowing of current between the drain and source terminal is to establish a channel. So establishing the drain and the gate at a positive potential with respect to the source. So VGS is some positive potential we are applying at the gate terminal, which will basically pressurize the holes. If this will become positive, so what it will happen? It will pressurize the holes which are present in this particular region, and the holes will move towards right. And the electrons which are available in this particular region, they get attracted near this SiO2 layer or between drain and source terminal. So as a result, as we are increasing the VGS values further, so it will attract more number of electron in this particular direction. So it creates a passage, basically it creates a path, and due to which there is a formation of channel. So we have the term that VGS is basically the minimum gate to source voltage is required for the formation of channel. VGS equal to VT, threshold voltage. It is the minimum gate to source voltage which is applied across the terminal so that the channel is formed. Means the operation will be possible, the current will be possible if the channel is established. So the working will be started when VGS is greater than 0, means some positive voltage, and some positive voltage value will be nearly equal to VT, threshold voltage. So what will happen? Means VGS we have applied positive. What will happen? Electrons are attracted near this particular SiO2 layer, and holes are being repelled away. As a result, there is a passage. Now if we are applying some VDS, if VDS is applied, that means this terminal is positive. What will happen? The electrons are attracted in this particular direction, and as these electrons are moving from source to drain terminal via channel, then there is a flow of current which is termed as ID, drain current. And since due to this proper insulation, the gate current IG equal to 0. So we can say that drain current is equal to source current IS, ID equal to IS, like this. So this is a situation when VGS is greater than VT and we have applied some VDS. We can write down here that when VGS is greater than VT and we are increasing the value of VDS. So as VDS increases, ID increases. Further, as VDS further increases, ID increases, Now we'll reach a point where the channel will become tapered. So further increasing the value of VDS will basically fix the current. The current will become fixed. It will become saturated. And we can observe in the characteristic part that it will be a saturated value or flat value. Now we can see here that as VGS increases, now we will be fixing the value of VDS and the value of VGS increases. That means we can observe here, if VGS is further increases, that means more number of electrons are attracted in this particular direction. And as a result, the width of the channel increases. And if the width of the channel increases, that means more number of our electrons are in the channel area, and as a result, ID increases. So the relationship here is that as gate to source voltage increases, the concentration of electrons near the SiO2 surface increases eventually, and we can say that the current further increases. So we have the definition of threshold voltage, the level of VGS, the level of gate to source voltage that results in the significant increase in the drain current is called as threshold voltage, and it is denoted by VT. Since the channel was absent when VGS was 0, we have observed this, and enhanced by applying some positive voltage at the gate to source terminal. So we can say that on applying gate to source voltage, the channel enhances. So this type of MOSFET is known as enhancement type MOSFET, because on applying the gate to source voltage, the number of electrons in the channel area increases, which enhances the value of current, which enhances the channel. Now we have VGS greater than VT, and we have fixed this particular value, means the channel was formed and VGS was fixed, but we are increasing the value of VDS. As I have already told you that this upper part will become more reverse bias, and as a result the channel will become tapered, because the reason is, if this part will become more reverse bias, that means the depletion region here will be wide in comparison with this particular region. So the channel will become tapered. This is called tapered. So further on increasing the value of VDS will not increase the value of current, and ID will become saturated. It will gain a saturated level. So we can see the characteristics again for the enhancement type. So we have two characteristics. First is between ID and VGS. ID versus VGS, it is called as transfer characteristics, and ID versus VTS, it is called as drain characteristics or output characteristics. So first of all, the transfer characteristics, we can clearly observe that whenever the gate to source voltage is less than threshold voltage, so we have seen that no channel was there, and as a result the current was 0. But further, if we are increasing the value of VGS, the current increases, because on further applying the value of gate to source voltage, it basically strengthens the channel. It will provide the width of the channel increases, and as the width increases, we can say that the current increases. So this particular curve, the transfer characteristics, is quite different from the depletion type MOSFET. Now we have the drain characteristics. So the drain characteristics, the explanation is quite similar. First of all, when VGS is, let's say, less than VT, what will happen? The current will be 0. So the curve will be basically touching this horizontal axis. Now we have applied some positive potential which is, let's say, VGS equal to VT, which is a marginal situation for the formation of channel. So we can observe that current will become, the very few amount of current is flowing from drain to source terminal, and it will gain a saturated value. Further, we are increasing the value of VGS. So as VGS increases, ID increases. So we can observe here that the curve is shifted in the upward direction like this, because the channel width increases. So initially we have the linear region like this, and afterwards we'll be having the saturation region, because the channel will become tapered, and if the channel become tapered, it will only allow a constant amount of current, a saturated amount of current to flow from drain to source terminal. So we have the region over here. This is the cutoff region, because the current is 0. Here the current will become saturated, so it is saturation region, and here we have the ohmic region, ohmic or linear region, and we have basically a locus also like this. So one more important thing is that this type of MOSFET only work under the enhancement type of operation. The depletion type MOSFET, the depletion mode of operation is not possible for enhancement type, because initially the channel was absent. So if the channel was absent, the channel has to increase. So only E mode of operation is possible. So this is also termed as E only MOSFET. E only MOSFET, because of the enhancement mode of operation. Now we have the P channel. The second type of enhancement type MOSFET is P channel. So for P channel, the drain and source terminal is of P type, the substrate or the body is of N type. We have the SiO2 layer over here, and with the help of metal contacts, we have defined the terminals. Now we need to remember that for N channel depletion type MOSFET, the channel was formed when VGS was positive. So here we can say that the channel will be formed when holes are being attracted towards this SiO2 layer. How can this happen? This can happen only when the gate is provided with some negative voltage. That means the VGS has to be negative here, and also VDS is negative. So whenever VGS is negative and it will gain a minimum negative value, which is equal to threshold voltage, we can see that there is a formation of channel, and once there is a formation of channel, there is a flow of current. Further increasing the value of VGS basically increases the width of the channel, and as the width of the channel increases, the drain current ID increases. So this is the operation for P channel enhancement type MOSFET. Now we can see the characteristic curve. So we can observe first the transfer characteristics, which is between ID and VGS. So this curve is a mirror image of N channel enhancement type MOSFET. For N channel, the characteristic curve was in first quadrant. Now this particular characteristic is in second quadrant, because VGS was negative here. And we can see that when VGS was 0, or when the value of VGS was less than VT, the value of current is naturally 0. And further, the value of current ID increases as we are increasing the value of VGS beyond VT. And next we have the drain characteristics which is between ID and VDS. ID versus VDS for different values of input voltage which is VGS. So initially when VGS is less than VT, so the current was nothing but 0. We can write down here also that VGS is less than VT. But once VGS reaches some potential which is nearly equal to VT, that means there is a flow of current like this. And when VGS further increases in the negative direction, so we have seen the operation part that current increases like this. So again, we have the linear region over here or the ohmic region over here, and we have the saturation region . This is the saturation region. Here, downwards when the current is 0, again we have the cutoff region. And towards left, we have the ohmic, or we can say linear region. So this is the characteristics of P-channel enhancement type MOSFET. Also here the VDS has to be a negative value, because we have seen that source was connected at higher potential as compared to drain. So this we need to remember that this axis is basically negative. Or we can draw this particular curve in second quadrant by making VDS negative. So whichever ways it is easier to draw, we can draw. In the first quadrant also by negative values we can draw. Now the symbolic representation for enhancement type operation. As we can see here that this channel, it is not continuous, means the this basically symbolizes that the channel was absent. So this is like this, it is not continuous. So this is a basic difference between the depletion and enhancement type MOSFET symbols. Also for N channel, the body is of P type. Here also P type. For P channel, the substrate or the body is of N type. So accordingly, the direction of current will be inward for N channel and it will be outward for P channel. So these two are the symbolic representation with 4 terminals: gate, source, drain and substrate. Whereas it will make a small assumption that substrate and body are substrate and source, body and source are internally connected. So we can combine, we can join this, and we are left with only 3 terminals: drain, source and gate terminal. So we have the symbolic representation for enhancement type MOSFET, whether it is of N channel or it is of P channel. So after this, we can see that what are the possible differences between enhancement and depletion type MOSFET. So first of all, in enhancement type MOSFET, as we observed that the channel was absent, means the channel will be formed during the operation phase, and in the depletion type MOSFET, the channel is permanently fabricated at the construction time. So the major difference, the constructional difference between depletion and enhancement is, here it was absent and here the channel was present. Now we can say that second point is, normally this device is off when VGS was 0. We have seen in the operation part also. So the current was 0, the device was off, but in this particular situation for the depletion type MOSFET, when VGS was 0, but if you have applied some value of VDS, so definitely there is a flow of current between drain and source terminal. So we can say that this device is normally on whether we have applied gate to source voltage or not. Now this MOSFET cannot conduct current when it is off, means when there is no current, ID is 0, it will not conduct. And this MOSFET, the depletion type MOSFET, can conduct when VGS was 0 also. We have seen. That's why it is termed as on device, this is termed as off. The device is off. Also, for enhancement type of MOSFET, we need some minimum value of gate to source voltage, which was termed as VT. VGS is greater than VT. To turn on this particular device, the depletion type MOSFET, as the name suggests, the channel was depleted. That means the gate to source voltage has to be some negative value. So, VGS is negative, that means the channel will become depleted, the channel will become narrow. Also, we have seen one major difference, that enhancement type of MOSFET can basically work under, it can only work in the enhancement type of enhancement mode only, whereas the depletion is having a flexibility to operate under both the modes, E mode and D mode, depending upon the values of VGS. If VGS is positive, then we have seen the enhancement mode of operation, and when VGS is negative, then we have seen the D mode of operation. So this device is having a flexibility to work under both the modes, whereas enhancement type of MOSFET can only operate in E mode of operation. Also, we have talked about it has no permanent channel, means at the construction phase the channel was absent, but in the depletion type MOSFET the channel was permanently there, means it was present during the construction part only. Now we have the applications. Generally, enhancement type MOSFET are used in the switching applications. As we are aware that JFET, the operation of JFET is slower. The JFET is a slower device. So, the MOSFET basically are used as an amplifier or as a switching operation also. Why it is best suitable for amplifiers? Because we have seen that amplifiers having this MOSFETs are having high input impedance. So if they are having high input impedance, that means they are perfectly suitable for amplification. So that's why the MOSFET are used as a amplifier. And also in the inverter circuits, they are also used in different motor drivers, digital controllers and power electronic ICs. It is also used in digital electronics, means we can have the logic gates also with the help of CMOS circuit, with the help of N channel and P channel MOSFET. We can have all the type of digital electronic gates. AND gate we can have OR gate also. So these are the application areas of MOSFET. These are the references